If you find DSA problems confusing or random, the real issue is not logic. It's that you don't know the patterns behind them. Once you learn these 11 DSA patterns, you will start seeing how 80 to 90% of lead code problems repeat the same ideas in different ways. Patterns are basically problem blueprints. They show you how to approach a question. Instead of solving each problem from scratch, you recognize the pattern and instantly know what tools or logic to apply. Learning these patterns saves hours of practice time, helps you write cleaner solutions, and most importantly, gives you direction when you are stuck. Let's break them down one by one. First one is two pointers. This is one of the simplest yet most powerful patterns. You use it when you deal with sorted arrays, linked lists, or strings and need to find pairs, move from both ends, or compare elements. Instead of using nested loops, you place two pointers at different positions, usually the start and end, and move them based on conditions. It's used for things like finding pairs that sum up to a target, checking if a string is a palindrome, or optimizing distance between elements. This pattern works because it cuts down the search space every time you move a pointer. It's mainly used when data is sorted or when direction-based movement helps narrow results faster. Some of the problems that can be solved using this pattern are two-sum 2, valid palindrome, and container with most water. Let's move on to sliding window. This pattern is used when you need to analyze a subset of data within a larger structure, usually a string or array. Instead of recalculating everything for each subset, you maintain a window that slides through the data, updating only what changes. It's perfect for problems involving substrings, subarrays, averages, or counts. For example, finding the longest substring without repeating characters or the smallest subarray that meets a condition. There are two main types: fixed window, like find max average of k elements, and dynamic window, like find longest substring with condition. Sliding window reduces brute force solutions from big O of n squared to big O of n, which is a massive speed up. Some of the problems that can be solved using this pattern are longest substring without repeating characters, minimum window substring, longest repeating character replacement, and maximum average subarray. Next one is DFS. DFS, or depth first search, is used when you need to explore every path in a tree before backtracking. You go deep into one branch before moving to the next. It's perfect for problems that involve path calculations, recursion, or backtracking, like finding a path sum or printing all paths from root to leaf. DFS is implemented using recursion or a stack. Think of it as go as deep as possible, then return. Use it when you need to do something for every node before moving up again, like calculating depths, searching for specific values, or generating paths. The key to mastering DFS is to understand when to go left, right, and when to backtrack. Some of the problems that can be solved using this pattern are binary tree in order traversal, maximum depth of a binary tree, path sum, binary tree, paths. Now let's talk about BFS. BFS, or breadth first search, explores a tree level by level. Instead of diving deep, you use a queue to process nodes in layers. First the root, then its children, and so on. This pattern is used when problems involve shortest paths, levels, or hierarchical traversal. You can recognize it when you are asked to return results level-wise or find something at the shallowest depth. For example, counting levels, finding the rightmost node, or checking minimum depth. BFS gives a structure to how you traverse data in a predictable order. Some of the problems that can be solved using this pattern are binary tree level order traversal, binary tree right side view, minimum depth of binary tree zigzag level order traversal. Now, let's jump to slow and fast pointers. This pattern is common in linked lists or sequences where you need to find cycles, middle points, or overlaps. You use two pointers moving at different speeds. Usually one moves one step, the other moves two. When they meet, you have found a cycle or midpoint. It helps detect loops efficiently without extra space. It's also great for problems like finding the middle of a list or checking palindrome linked list. The beauty is its constant space usage and linear time. Whenever you have a sequential structure and need to detect relationships within it, this is your go-to pattern. Some of the problems that can be solved using this pattern are linked list cycle, middle of the linked list, happy number, and palindrome linked list. Now moving on to binary search. Binary search is the backbone of many efficient algorithms. You use it when data is sorted or can be divided logically into halves. The idea is simple. Repeatedly split the search space in half until you find your answer. Instead of scanning every element, you focus only on the half where the answer could be. It could also apply to problems not directly about searching, like finding a boundary, minimum or maximum value that satisfies a condition. When you can say the answer lies on one side of a midpoint, binary search works. Some of the problems that can be solved using this pattern are binary search, search in rotated sorted array, find minimum in rotated sorted array, and search in a 2D matrix. Now here comes dynamic programming. Dynamic programming is all about breaking a problem into smaller subproblems and using their results to build the final answer. You use it when a problem has overlapping subproblems and optimal substructure, meaning smaller results help from larger ones. Instead of recalculating repeatedly, you store immediate answers in arrays, tables, or maps. DP problems usually start with recursion, then get optimized using memoization or tabulation. You'll see this pattern in problems involving choices, combinations, or sequences, like finding maximum sums, counting ways, or minimizing cost. To get good at DP, focus on identifying states and transitions, what each index or variable represents. Must-do problems are climbing stairs, house robber, coin change, and longest increasing subsequence. Now let's talk about top K pattern. You use this pattern when you need to find the largest, smallest, or most frequent K elements. It's common in data stream, ranking, or frequency-based problems. The key tool here is a heap or priority queue, which keeps track of the top or bottom elements efficiently. You push items into a heap, and when it exceeds K, you pop the least relevant one. This keeps your space usage small while maintaining order. It's a must-know pattern for problems involving rankings or nearest points. Must-do problems are kth largest element in an array, top k frequent elements, find k closest elements, and k closest points to origin. Now let's move on to backtracking. It is used for problems where you need to explore all possible combinations or configurations. It is a depth-first approach where you make a choice, explore further, and undo the choice if it does not work. It's perfect for subsets, permutations, combinations, and constraint-based setups. It's like trying all possible paths until one fits. You can recognize it when the problem involves generating or counting possibilities. The main trick is pruning, avoiding unnecessary exploration once a condition fails. Focus on defining the state, the choices, and the stopping point. Must-do problems are subsets, permutations, n-queens, generate parentheses. Now here comes monotonic stack. This pattern is used when you need to find the next or previous greater or smaller element in a sequence. You maintain a stack that's either increasing or decreasing so that you can process elements efficiently in one pass. It's common in problems involving ranges, spans, or heights, like finding next greater temperatures or largest rectangle in a histogram. You can recognize it when the problem asks about the nearest element that satisfies a condition. Monotonic stacks reduce complexity from big O of n squared to big O of n by maintaining order and removing elements no longer useful. Must-do problems are next greater element 1, daily temperatures, largest rectangle in histogram, trapping rainwater. Now last but not the least is union find. Union find or disjoint set union is used to group elements and quickly find whether two belong to the same set. It's powerful in graph problems that involve connected components, networks, or cycles. You maintain parent pointers for each node and use two operations. First, find to get the parent, and second, union to connect two sets. Union find helps detect cycles, count islands, or merge accounts efficiently. Whenever you deal with grouping or connectivity, this is your go-to pattern. You will see it a lot in graph and network-based questions. Must-do problems are number of islands, accounts merge, redundant connection, number of connected components. So, these 11 DSA patterns are like shortcuts to understanding problems. They repeat again and again with different names, but the logic behind them stays the same. If you are just starting, begin with 2 pointers, sliding window, DFS and BFS. They appear in more than half of all beginner level questions. Once you are comfortable, move to fast and slow pointers, binary search, and dynamic programming. They form the next layer of logic. Finally, learn top K elements, backtracking, monotonic stack, and union find or advanced patterns. Don't focus on memorizing code, focus on recognizing what's happening. The moment you can look at a question and say, oh, this looks like a sliding window, or this is clearly a DP, you have already done half the work. That's how good problem solvers think. They don't guess, they map the problems to patterns. Master these 11, and LeetCode will finally start to feel easy.